Hey guys, your boy Chiller here. Welcome back to C++, doing some multi-threading stuff here. Fun times. In the last video, I just showed you how to launch a bunch of threads, and we got some good performance enhancement for our troubles there. But now I want to take a little step back and just look at the different kinds of scenarios, different styles of multi-threading that you might come across. And yeah, so I'm going to be drawing. You're going to get some high quality chili diagrams today. And you know it's a good day when you can get some chili diagrams. Yeah, in the last video, what we did was we had a large data set. Let me just, let's draw blocks and lines and rectangles. And let's put boxes in those rectangles like this. You know what I mean? So these are our data sets. These are our 4 data sets. These are our ints. We got a bunch of data, and we crunched them. And we could crunch them by using one thread, and going like zoop, 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 a zoopity doop, and that took like 400 milliseconds. Or we could go with one thread. We could go zoop, and then with another thread we could go zip, zap, zoobity bop, and we do these 4, and we do that all at the same freaking time, and wouldn't you know it, it's like 4 times faster because we were doing it with 4 threads at the same time, and that's a beautiful thing. So I mean, that's what I think most people think of when they first think of multi-threading. You got a big task, got a lot of work, you divide it up, you reduce the total time to complete that work. That improves your performance. That means you can go home earlier. That means you render more frames per second, and you get the silky smooth graphics. You know what I mean? Yeah, this is like the simplest, most commonly perceived use case, in my opinion. Even though it's kind of simple, it can get complicated. It can get very complicated, and we're going to go over that in the future. But I mean, in this case here, processing this data set here has nothing to do with this data set here. It doesn't refer to that data. It doesn't refer to the results of the processing between these 2 data sets. They're completely separate. And so we have a term for that. It's called embarrassingly parallel. But in the real world, things are often not that easy. I mean, this is not a case that is super uncommon. Many times you will have, stuff that is embarrassingly parallel and that you can just easily throw like a bunch of threads at and, times in your performance. But many times it's not. Many times the results in some of the processing in here will depend on the results of other processing here, or you'll have to combine the results of these 4 into like a single one, which is not too hard, not too bad. It's worse when your data processing is, sharing the same space in memory, and maybe they're both trying to modify the same memory, and that causes very bad issues, and you have to work with synchronization between your threads, and if you get it wrong, bad stuff happens. It's not fun. So that's one way things can get tricky. Another way is if your data sets aren't all the same size and you don't really know the size ahead of time. I mean, let's say you have 40 work items, but each work item is uneven. So if you just divide up the work items, okay, you get the first 10, you get the second 10. If this one of the work items are like this big, and there are 10 of them, and in this one they're like this big, what you're going to have happen is this thread is going to be finished way faster than this thread, and it's just going to sit around with its thumb up its butt while this thread has to work on a huge data set because they were uneven. So that's another thing that you got to worry about. And there are other things, like in this situation, all the data to be processed is available at the start of processing, and we just use it. But a lot of times data is coming in on the fly, and then we have to process it. And so generally we have queues, and we divide it up, we dispatch it to different threads, and there's more, you got to orchestrate that. So there are plenty of ways in which this style of multi-threading can be complicated. And, you know, we're gonna look at them. That's what we're gonna be looking at in the beginning of this series. Because I think it's, you know, it's an interesting use case and it's what a lot of people are interested in. In this multi-threading paradigm, the goal is you've got a lot of work to do. You've got a CPU with, you know, multiple threads. And you want to maximize those threads. If you're only running single-threaded, you're only doing, like, you know, if you got 4-core CPU, you're only doing about a quarter of what you could be doing if you were multi-threading. You want to maximize the usage of your silicon. That's what the whole goal of this. So, I mean, that means that if you are using a CPU with only one core, you're going to get no benefit out of multi-threading in this scenario. And if you have a CPU with 4 cores, you're not going to get, you know, benefit generally by launching 20 threads and trying to divide your work up into 20 data sets because you only got 4 workers. So generally you want about 4 threads. Of course, depending on the data set, I'm not going to get into this, but you know, CPUs might have 4 cores, but they might have 8 logical processors. So each core behaves like 2 cores, and that's because of something called, I actually forget the name of the term. I don't think it's symmetrical multiprocessing or something, but I mean, Intel calls it hyperthreading, right? It's hyperthreading. So it's running 2 cores at the same thread at the same time, so that if one of these guys is blocked, usually due to a memory access, the other one can still be running. And it's much faster than using the CPU or in the operating system to switch contexts for threading, but whatever, who cares about that? That's just, it doesn't matter. We're not gonna think about the existence of hyperthreading. Sometimes it's good, sometimes it doesn't help, sometimes it even makes things a little bit slower. So forget about it. 4 cores, we use 4 threads, and that's how we're gonna live our life. But anyways, yeah. So this is gonna be type number 1. Let's just call this bulk parallel processing. I hope I put the double L's in the right place, but you get the idea. Whatever. Number 1. This is number 1. All right, what's number 2? So sometimes you have, you know, you have processes, you have things that you do, and they take a while to happen. Like, not because the CPU is working, but because it just like takes a while for the result to come back. The main one is obviously communication, you know, TCP IP. You got a socket, you send out packets, you wait for a response. It's going to take some time. It's going to take, you know, tens, if not hundreds of milliseconds. And while you're waiting for that, if you need that result to do the next step of processing, you're just sitting around twiddling your thumbs. So these are these weighty boys. It's a technical term, but I'll dumb it down for you. We'll call it async. You know, two in the pink, 1 in the async. So like, let's say you've got like some processing, and we can break it down into stages. Stage A, B, C, D. And each of these stages is characterized in that it requires some kind of communication with a remote host or whatever. And so it's going to send out some message, it's going to get some response, it's going to do some processing, it's going to feed that into stage B, which is going to, you know, do that stuff again, and in C, and in D. Right. So in each of these stages, going to be a lot of waiting time. Like perhaps, let's just make this up here. Let's say the latency to your host is, you know, 40 milliseconds. So maybe the processing in each of these stages only takes 0.1 millisecond, but it takes 40 milliseconds to actually get the response. So a very small percentage of the CPU time is actually doing work. The rest of it is just waiting with its thumb up its butt. But what are you going to do? You can't proceed to do the next work until you got the response. It's a requirement. The processing of B depends on the result of A, which depends on the communication. So you have to wait. So what are some of the ways that we could solve this problem? Because if we just wait, our CPU is sitting around for like 160 milliseconds doing nothing. It could be doing other work, you know. Theoretically, maybe you've got other stuff going on. You've got a UI that you've got to render, or I don't know what you got to do. You got to do things. You're busy. You're a program, but you're sitting around waiting for packets. That sucks. So imagine what's happening here. Okay, so when we're receiving data, we're going to call like a function receive on our socket, and that function is going to block until it receives data, and then it's going to return that data, and then we can process it. What if instead of calling this blocking function, we called like a function check receive? And what this does is it just checks to see if there is any data that we can, read. And if not, it just returns a true or false. If there's data, it's true. And then if you call receive, it won't block, it'll just return data. If it's false, that means there's no data. If you call receive, it is going to block and you're going to be stuck until some data comes in. So we can use this to poll for data. And now, instead of waiting on A and B and C and D for data to come in, what we could do is we can run our program where we do some processing, we send out a packet, and then we check to see if there's a response. And if there's no response, we do some other stuff. And after we do a little bit of other stuff, we come back, we check again. Okay, is the data there yet? No. Okay, we're going to do some more other stuff. And then we're going to check, is the data? Oh, the data is there now. We're going to receive it. Then we're going to process. Then we're going to send another packet. And then we're going to check, but it's not there. So then we're going to do some more work. You get the idea? So what you would do in this kind of situation is maybe you'd build like a state machine. So we would have a variable state, and it would tell us, are we in stage A, are we in stage B, C, or D? And then you do some processing, you run your state machine says we're in state A. So we're going to send a packet, and then we're going to exit the state machine. We're going to return from the state machine run function. Going to do some more processing. We're going to call state machine run again. State machine run says, okay, the state we're in is we're waiting for data from A, so we're going to call check, no data. So we return, we do some more processing, we call run on our state machine. Our state machine says, okay, we're going to check. Oh, there's data. Let's process it. Let's proceed to state B. State is now B. Then send. Then again, process, run the state machine, check for data. No, again, you get the idea. This is annoying. It's annoying. You got to turn what could be like a simple thing of like call function A, call function B, C, D. Now you got to build like a whole state machine, and it's a whole thing. And then you got to have like a loop in your main body where you do some processing, and then you call run on the state machine. And then you got to get, when this is finally done, you've got to get this result out of the state machine into your main program flow. It's that whole thing, man. I don't want to do that. That sounds like a nightmare. Now, luckily, nice programming languages have things called coroutines, which can actually, what they can do is they can allow you to write code like this, which is just A, B, C, D, and it'll automatically turn it into a state machine and handle all that machinery for you behind the scenes. That's pretty sweet. That's called, did I say it was called coroutines? Yeah, so like in C#, you've got like async and await. That's basically state machines. And we also recently in C++20, we got coroutines into C++. But we only have the base low-level language support. We don't have any neat utilities to use them. So it's kind of mind-bending to create coroutines right now. But eventually, we're going to have that. Another way to do things, this is the way that I believe like old-school JavaScript would do it, is let's say you would call receive, and you would pass it a function. And the function would be the processing that you do when you receive the packet. So the function would take a packet, and what happens is now in the back end of the engine or whatever, JavaScript, you register this function with this thing, and when the packet comes in, it will automatically call this function. So this receive function that you call, it returns immediately. But that doesn't mean that you've received anything. You've just said, okay, when the packet comes, process it using this function. And then in the back end of JavaScript, it keeps track of all these, callbacks. And when things happen, it will dispatch for example, the packet information to this function, and it'll be executed. And that's okay. And you have this thing in C++ as well. Socket libraries, they often have two modes. One mode is blocking. And it's like this. You call receive and it will block until data comes in and you process it. And the other one is callbacks, asynchronous. And yeah, you give it functions and then it'll call that function. But let's say you've got this situation of A, B, C, D. So what does that look like? Well, I want to receive, and we're going to pass it a function f. And f, what's it going to do? It's going to do some processing, but then it's going to send, and then recv, it's want to receive data and process that data. So that's another function inside of this function. And then that function is also going to send an recv. You get what I'm saying? You got functions inside of functions, inside of functions, inside of functions. This is referred to as callback hell. And I'm not joking. I didn't make this up. This is actually what people call it because it kind of sucks. It gets very confusing, especially when you start throwing in error handling and stuff like that. It gets very mind-bendingly just hateful, and nobody likes it. Nobody likes callback hell. So it sucks. But it's one way of solving the problem. You've got state machines, which are very nasty to implement yourself, but which can be kind of sexy if you've got compiler support. You've got callback functions. You've got things in between with like, later on in JavaScript, you got like promises, which are kind of sexier syntax wrapping around this. But these are ways of solving this problem. However, another way of solving this problem exists, and it's called using a thread. So I'm going to show you that because I'm talking about threads. Not specifically because it's, using threads to solve the problem is superior to these other methods, just because I want to show you ways of using threads. And the way you do it is you have your main thread, and it's going to do stuff, and it's going to do stuff, and then it is going to launch a thread, and that thread is going to do your A, your B, your C, and your D, and is going to do that stuff by calling receive, which is a blocking function. But it doesn't matter. What happens when we block here? Oh, so this thread is blocked. Fine. The CPU scheduler, the operating system, says, okay, this thread is blocked. We're going to give CPU time to a different thread. So now you're not wasting time. You're not clogging up your main thread. Your main thread is doing its own thing. This thread, when it waits, and other things run on the CPU. And then when this thread is received and it's ready to do stuff, then the operating system says, okay, it's your time to shine, thread 1, do your thing. And then thread 1 does some more thing, and then it waits again. And then the operating system gives the core to another thread, another needy thread in need of CPU time. So what this is saying, when you have multi-threading to solve this problem, is instead of us wasting our time building state machines to schedule what stuff the CPU is doing or what stuff the core is doing, or having callbacks and then having some kind of central scheduler that calls the callbacks when the time is right, just let the operating system do that. Let the operating system and the hardware take care of that scheduling. And we can just call very easy to understand functions that block until they actually have the result. There you go. That's threading for asynchronous problems. And maybe the main thread here, it does a task, launches a task. Thread 1, another task, another similar task. Thread 2 also does an A and a B, and so on and so forth. And you can launch multiple of these bad boys, and they can all be running. You can have, maybe 10 or 20 threads running, and they're all doing their thing. And when they're waiting for data, they just chill out, and the CPU gives the cores to other threads that do need to do processing. And it's beautiful. It's a beautiful thing. Let the hardware and the OS take care of all that annoying scheduling BS, and we can just focus on making a cool thing. Now, I want to say one thing. This does This definitely contrasts with, type 1 of multi-threading that I showed you. In type 1, we have 4 cores, and we want to make sure that those 4 cores are working 100% utilization. We want to throw work at all of them so that our work gets done faster. In this one, type 2, we don't really care. I mean, most of the time that these threads are alive, they're just spent waiting. We don't care about maximizing the utilization of our cores here. All we care about is just, having a single thread of execution to manage this state here so that we don't have to do it ourselves with logic. We can just have this thread run its process A, B, C, D, and scheduling is all managed by the CPU, by the OS. So whereas in type 1, you would never do that if your CPU, if your system only had 1 core. In type 2, you would definitely do this even if your CPU only had 1 core, because most of the time all these threads are just sleeping. So even with 1 core, it makes sense to do this to manage, some asynchronous processing. There's differences between the different applications of multi-threading there. Type 3. So I call this one needy knob. So what's this? Well, my example for this would be your sound card. It's playing out audio based on samples that are stored in a buffer. If your audio is like, let's say 44 kilohertz, then you're going to consume samples out of here, maybe like 200,000 samples per second. Bytes per second? Sure. 200 kilobytes per second of data. Now, what happens if this buffer empties? You get no sound. The sound just cuts off. So if you were in like a wave, and then you're like this, and then it immediately cuts off, it's going to go to 0. That's going to sound like bleh. It's going to sound bad. It's going to make like a popping sound. So what happens if your buffer is being filled and then emptied before empties out completely, and then is filled a little bit and then empties out completely? You're going to get some sound, and then like some 0, and then some sound, and then some 0, and then some sound, and then some 0. And let me tell you, that sounds like it doesn't sound good. And I know this from experience because I had a computer. My first, real PC was a AMD K6-2 made by the fine people at Paradigm Computers. And whenever you're surfing the internet on Internet Explorer, as you do, you scroll the page, and if you're listening to an MP3, it goes blah, blah, blah. Why? Because it takes so much CPU power to scroll the graphics of the page that the processing that fills this buffer stalls, and the buffer empties out completely, and then you get this. So that's a needy knob. Why is it a needy knob? Because this buffer, it has to be filled continuously. And you might say, well, chilly, just make like a really big ass buffer, and then even if there's a long wait between fill sessions, if you want to call it that, it's fine. It won't empty out completely. But you can't do that because if your audio, the length of your audio buffer determines your audio latency. If it's very long, if I put something in at the end of the buffer here, it might take 4 seconds before it can come out to here. That means that I have 4 seconds of latency, which is very bad. Like, just in general, like in a UI, if you press something and it's supposed to ding and it dings 4 seconds later, that's bad, obviously. So you can't have huge buffers. You need small buffers, and you need to fill them all the freaking time. And that means you got a needy knob. So this is an example of something that you would want to do with a separate thread. Because if you had just a single thread and you had to do a whole bunch of things, you had to draw your screen and you had to, process your physics, and you have to, do your networking. In between here, you also need to make sure this buffer doesn't empty. So you'd have to insert function calls to fill the buffer in between all of your operations. Your code would be littered and interspersed with buffer filling function calls. That's dumb. That's obviously dumb. And if any one of these single function calls in between your buffer filling calls, it takes too long, and your audio is going to sound like blah, 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 blah. So, no, you don't do this. You have a separate thread, and this thread's only job is to wake up, every 2 milliseconds and fill some more data into this buffer and then go back to sleep. So mostly it's sleeping. It wakes up every 2 milliseconds. It works for 0.08 milliseconds, and then it goes back to sleep. And then it wakes up and it does a little bit of work and then goes back to sleep. This is the kind of thing that you want to do with a thread, not the kind of thing you want to figure out how to do in a single thread. Very bad idea. But anyways, yeah. So needy knob, that's number 3. And honorary mention, number 4, is organizational. So this is kind of a thing. It's not like you have a big single work set that you're dividing up. It's not asynchronous. It's not a needy knob. What it is, you've got a whole bunch of different systems that are mostly, they interact with each other, but they're mostly separate. Let's say you've got a game and you've got, physics, and then sound, and then graphics. And, you put these systems on separate threads. And it's organizational. You get a little bit of performance benefit, but usually what ends up happening is one of these is going to be way bigger than this one and this one. So this one's consuming all of your time. And if you're only running 3 threads, one for physics, one for sound, one for graphics, you're not going to get much of a benefit because most of it's just graphics anyways. So these ones will finish very quickly, and you're offloading very little work to these different threads. Most of it is just on a single thread still, which is the way a lot of games actually work. They technically have multi-threading, but really they're just offloading very small separate systems, and for the most part, most of the work is still being done on a single thread. But anyways, I digress. It's a way of, multi-threading, and it's an easy way to, separate concerns. It can be useful. Here's the thing. Imagine you've got a user interface. It's a separate system. So you run it on a separate thread. And that's good because what if you're running everything on a single thread and you're doing some processing? We'll call it physics, but it could be a calculation. Like a accounting calculation or something. I don't know. It doesn't matter. If this calculation takes a long time and you're not servicing your UI, it's going to freeze for the user, and that sucks. And we've all used programs where that happens. You're doing some long process and the whole UI freezes up. It's dumb. So in that sense, you definitely want to split your systems up. Also, in that sense, we can also kind of see this UI as also a kind of needy knob in a sense, because you have to service the UI at a fairly good rate. Otherwise, it's going to start to, lag for the user, and that's going to suck. Which brings me to another topic, which is these 4 categories that I'm just pulled out of my ass. These are categories that I just pulled out of my ass, meaning that, don't take this as the Bible and you're trying to figure out, okay, am I type 1 or am I type 3? Because it's all shades of gray. And I just made this up to kind of conceptualize multi-threading in a way where you can kind of see the different applications of it. And, when you're looking at a problem, you can get an idea maybe how to categorize it. But just like we've shown here, you could look at UI as just organizing separate systems on separate threads, but you could also look at it as a needy knob that needs to be serviced at a regular interval. Many real-life problems are going to display features from more than one of these categories that I've shown. They're not completely mutually exclusive. They're not all black and white. And as I mentioned before, I pulled them directly from my anal sphincter And so, yeah, take it all with a grain of salt. But I think this is an interesting and useful way of thinking about multi-threading, and it might, facilitate future studies. And that's it. That's all I wanted to say in this video. I was talking and making really bad drawings and sometimes misspelling words, probably. I don't know, maybe. But anyways, next video, if I can, ooh, this is getting very nasty. Next video, we're going to be looking at, type 1, bulk parallel processing. We're going to be looking at for, several videos whenever I get time to add videos to this series, which will, depend on how much interest there is in videos in this series. But yes, I will be making videos and we'll be looking at a whole bunch of things. We'll be looking at scheduling, this bulk parallel processing, breaking problems down into task units and dispatching them to worker threads, thread pooling and synchronization between threads, definitely. Things like mutex, condition variable, all the good stuff. It's going to be a good time. If you liked the video, if you want to see more in this vein, click the like button, subscribe, leave a comment, buy my merch. I don't have merch, but if I did, you should definitely buy it. Anyways, yeah. So I'll talk to you later. Have a good time. This was C++. Wait a minute. What is the thing I always say? Thanks for watching. Hope you enjoyed this video. Please click the like button. I always said that part. And I will see you soon with some more multi-threading. There you go.